Ziqiang.
So it's Dr. Feng actually received his PhD from Carnegie Mellon University. Well, he studied mobile edge computing and machine learning application. He's currently a software engineer at Google. His interest includes distributed system, database, and machine learning performance. And with that, let's welcome our first speaker on his interesting talk.
Testing. Okay. Good morning, everyone. Feels a little bit nervous. Suddenly got bumped to the first one. So my name is Ziqiang Feng. I'm currently a software engineer at Google. Previously, I got my PhD from Carnegie Mellon University, where I did this work with my advisor, Satya. So today is my great pleasure to present our work, Semantic Fast Forwarding for Video Training Set Construction. In 2020, 700,000 of video is being shared online daily from a wide range of data sources, such as public surveillance, dash cams in your cars, and drones. And there's a lot of high value seen in analyzing this video data to detect some valuable and interesting events happening, right? So for example, for the purpose of insurance, for city planning, or for law enforcement. When it comes to analyzing video data, what comes to many people's mind may be object detection. And indeed, object detection has actually become pretty mature these days and reliable. However, some concepts are temporal in nature and cannot be inferred by just looking at a single frame. So for example, if you want to detect some person getting out of a car instead of getting into a car, you cannot just tell by looking at one single frame in the middle, right? You need to look at the whole sequence to understand the spatial and temporal relationship between these objects to know whether he's getting in or getting out of the car. Now, this problem is generally dubbed as activity recognition in the computer vision community. And the state of the art in this area is to train large deep neural networks using a lot of labeled training data. Our work actually focuses on this part of the problem, a lot of labeled training data. How do we obtain this efficiently? Now, note the keyword here is not only a lot, but it's also labeled. You need to label a lot of data. So let me just show you how we are doing this today. This is how we do it. Unsurprisingly, labeling video data at the moment requires a lot of intense human labor. And actually, people see business opportunities in it, and it creates an industry. You basically hire dozens or hundreds of people to annotate the data, to watch the video, and annotate the time and space of all the events in it. Can we do better than this? That's the focus of this work. In this paper, we make the following contributions. We introduce the concept called semantic fast forwarding, which basically means you programmatically incorporate human heuristics in the labeling system and use it to fast forward the video to the probable video segments of activities so that the human labeler does not have to watch all of the video data indiscriminately. And our methodology unifies DNN-based object detection on individual video frames with entity relationship reasoning in both spatial and temporal dimensions. We built a system called Eureka to implement this idea, and we evaluated it on realistic untrimmed video data. So in Eureka, we express a heuristic about an event by using an event stream programming abstraction. Let me describe the key concepts in this framework by walking you through a concrete example. Let's say we are trying to detect the event where a person is biking through a red light. The first key concept in Eureka is called event, which is basically a data structure that includes temporal bounds a spatial bound, the RGB data within this bound, and all of the metadata that you computed and extracted from the RGB data within this bound. So for example, if you run object detection on all of the video frames, then each instance of a person is actually essentially an event. The next concept is event stream, which is straightforward, which is a stream of all events of the same type. So in this figure, each row here actually represents an event stream. And finally, by using a variety of event stream operator, we can construct representation of more complicated events in terms of simpler events. So for example, after detecting all the persons and all the bytes in these video frames, we have two primitive event streams called bytes and persons. And then by running a join operator between these two input streams, using the overlap predicate, we generate a bicyclist event stream, which represents all of the bicyclists appearing in the scene. Similarly, we can detect the appearance of red lights in each individual frames, and we group them together into causal gray events called periods of red lights. And lastly, we can join these two, again, using a temporal predicate called during, where we find the periods where you've seen a person biking through a red light. Now let me give you another example. This is the example I mentioned earlier. Suppose we are trying to detect a person getting out of a car. You can think for a second, how will you describe your heuristic about this? In particular, I invite you to think about how will you distinguish it from a person getting into a car, or a person standing next to a car, or a person just walking by a car. And here's one way to do it. Again, we start by running object detection on the individual frames. Then, by grouping these car detections together, we construct an event called a stop car. Now, note that it's not just a car event, but it's a stop car event, because we notice that this car's position has not moved across the frames. And similarly, using some sort of tracking algorithm, we can construct a person's trajectory by merging these together. So this basically forms a curve over a certain time span. And lastly, we do a join between these two events using two conditions. The first condition, person begin time during stop car time interval, basically means the point of time when this person first appears in the scene, a car must be stopped there. This is a temporal condition. The second condition, person begin B box within stop car B box, which means when this person first appears in the scene, he appears from where the car is. So basically, these two conditions says, I want to see a person whose first appearance in the scene is from a car, and then he goes away. Now, the pictures I show here is actually a zoom-in instance in the wider scene. The real-life data we're talking about, the real-life data we're dealing with is data that looks like this, right? You may have multiple cars in the scene. You may have multiple people walking around in different directions. And there are many pairs between cars and persons. And they form different kind of temporal and spatial relationship between them. And using the programming abstraction, we are able to filter out all these pairwise relationships and identify the ones like this. So for evaluation, we use two datasets, the VRED dataset, which is a real-life public surveillance, and the Okutama dataset, which is a drone view dataset with scripted activities. Now, what I want to highlight here is that we focus on untrimmed and uncropped multi-activity video data instead of fixed-length single-activity video data, because in the computer vision community, there are a lot of data sets where each file is 3 seconds long and it has been cropped into a single person performing a single activity in the center of the screen. That's not the kind of problem we're tackling here. How to improve the performance of DNN models on that kind of data is the computer vision community's problem to solve. However, you can imagine a lot of effort has actually been spent into collecting and curating that kind of data set, and that's the problem we are tackling here. Also, before seeing the results, it's important to talk about metrics. I want to remind you again how this whole scenario works. So we have a bunch of video files or video streams of variable lengths coming into Eureka, where we inject it with programmed heuristics. And Eureka will emit a number of variable length segments of videos. The labeler will watch this video and then annotate all the event instances she sees in these segments. Now, if you think about this, traditional image metrics such as precision or recall are not applicable here. First, these video segments, these emitted segments, they have variable lengths. Some are shorter, some are longer. So it's not fair to just count the number of them, just count how many of them. And second, some of these segments may contain multiple events instances, while some may contain none. So again, it's unfair to just mark each single one of them as either positive or negative. So instead, we make our metrics based on two basic assumptions. Assumption one, positive examples are rare, while negative examples are abundant in this data. So we should focus on counting positive examples. Second, labeling cost is measured as the time spent by the labeler sitting in front of a computer monitor, watching this video and annotating this data. And after all, if you run a business of data annotation, this is the metric by which you pay your employees, right? So based on this, we define these two metrics. The first is called productivity, which is the number of event instances discovered in the return data divided by total length of the return video, which basically says something like, oh, for each hour I spend on watching this video, I can find 5 events. And second is event recall, which is the number of event instances discovered divided by the number of ground truth event instances. And we evaluated using 6 events in the 2 data set I just mentioned. For the high order bit, you can first focus on the event recall column and the productivity column. And we compare 3 approaches. The first is brute force, which is obvious. FB Eureka stands for frame-based Eureka, which is basically Eureka's implementation of many previous work that employs frame-level heuristics. So if you want to detect a person getting out of car, you filter all the frames by detecting persons and cars in the frames. And event-based Eureka, EB Eureka, is what we propose in this work. Now, not surprisingly, brute force always gives you 100% event recall. That's by definition. As we move to more descriptive methods, inevitably, we will have a loss in recall. And that's because all these methods need to use computer vision building blocks, which are not perfect. EB Eureka will have additional loss in recall because we need to use additional computer vision techniques such as tracking, which again is not perfect. However, we notice substantially improvement in terms of productivity that outweighs the loss in the recall. Also, you may notice that the Okutama dataset seems to be a lot more harder than the VRAT dataset. And there are mainly 2 reasons. First, the zone wheel in this dataset makes object detection harder on a frame level. And second, this dataset is scripted. All activities are scripted and staged so that the activities are more dense in dataset and there's less headroom for fast forwarding in this video. But this result actually gives us more confidence because, after all, we are targeting real-life scenarios such as the ones presented in VRAT. So in the interest of time, I will just put up the conclusion slide here and welcome any questions.
do have a couple questions. So I will start with one. So it's interesting to see in the last slides that you show there is a trade-off between recall and the increased productivity, right? So I was wondering whether you could give some intuition in terms of how such trade-off can be made if you're, let's say, a business owners for data labeling, business, right? So how would you justify what is the reasonable recall you're aiming for? Are there any two knobs you could provide from your Eureka's perspective for those owners?
Yeah, thank you for the question. So, I would say, first, inevitably, there will be a trade-off between recall and productivity, unless you have a perfect solution. What is the best trade-off? What is the sweet spot? I believe is really case by case. So I don't think there is a universal gold standard for the right trade-off to make. But the high order bit here is that what Eureka offers is a larger trade-off space, which allows you to pick more points. So basically, if you think about it, frame-based Eureka can be seen as a reduced form of event-based Eureka, right? You take any event-based Eureka, you remove the temporal component from it, you get frame-based Eureka. So essentially, Pirate, we extend the search space on top of what Pirate has offers and allow business and people to make choices in the larger trade-off space. And again, what is the best trade-off you're targeting at? Probably depends on the actual use case, whether you're law enforcement or you're for business purpose, there's probably a different trade-off to make. Thank you.
Hi, Karthik from University of Buffalo. So a couple of questions. So the first thing, you mentioned something about the programming API. So in this case, the example you've given is to go from object recognition to activity recognition.
Yeah.
But your programming API seems to be somewhat proximity-based. Have you thought about more other things you can do with that sort of, what other types of events can you detect or identify automatically of the kind? That's the first question. The second question, I can't imagine computer vision folks haven't done this already. So your temporality is basically some version of using learning over video, right? So instead of comparing it frame-based Eureka, have you thought about comparing with other vision techniques that do this style of real-world activity recognition, and how would that compare?
Yeah, so there's a lot. There are two questions. So first question, we will consider incorporating more of what I call backbone in the system. So what I mean backbone in the slides I present here is object detection. So it's sort of the computer vision backbone. And we run further temporal spatial reasoning on top of this backbone outputs. I can imagine other backbones will be incorporated into the future, such as, to give you an example, human pose estimation, which allows you to detect human actions using that kind of information. Second one, let me try to be brief for the sake of time. Second one, if you look at a lot of these state-of-the-art papers from the computer vision community, the overwhelming majority of them still seems to be, give me a lot of label data, and I will train a fantastic network for you. And that's what they're good at. And what we are trying to solve here to how to get this data more efficiently and cheaply. I wonder if we still have time for more questions.